Is it visible, students?
Yes, ma'am.
Yes, ma'am.
Okay. Let us start today with the next point, that is analysis of doubly reinforced beams. In the previous lecture, we have learned about how to calculate the moment of resistance of rectangular singly reinforced section. We have seen the derivations for XU expression, that is the depth of neutral axis, how we are finding for singly reinforced section, then how we are calculating moment of resistance, and we have also solved some numerical examples in which you first identified the type of the given section, whether it is under reinforced, over reinforced, and accordingly you calculated the moment of resistance of the section. Today we will see the next point, that is how to calculate the moment of resistance of rectangular doubly reinforced section. Before going to that, let us understand what is the meaning of doubly reinforced section. A beam or a slab, when it is reinforced with main steel, both in tension and compression zone, it is said to be a doubly reinforced section. You have seen the diagram or cross-sectional view of a singly reinforced section, in which we have seen the reinforcement in the tension zone only. But sometimes we need to provide this reinforcing steel or main steel in the compression zone also. In that case, that specific section is called as doubly reinforced section. Now, why we need such type of sections? We have to provide doubly reinforced sections in certain situations, like when the depth and the width of the beam is restricted and the beam has to resist greater bending moment than the singly reinforced beam. Now, if you recall the expressions for MUR, that is the ultimate moment of resistance given by the beam, it consists of the area of the steel term, AST term, right? So if it also consists of other parameters like depth and width of the beam also. So if we cannot change the depth and width of the beam, see, if the moment acting on a beam is higher, obviously we have to provide a higher dimension beam. Okay, so that whatever the external moment is acting, it will get resisted by the internal forces developed in the section. Now the internal forces, force of compression Cu and Tu, those are calculated based on the dimensions of the beam and what is the amount of steel we have provided in the beam. Now if the dimensions of the beam cannot be changed because of the some restrictions against the architectural view or the architectural um, um, appearance related issues, we need to provide a restriction to the depth and width of the beam. In that case, if the bending moment acting on a specific beam is higher and if we are not able to increase the dimension of the beam, we need to increase the amount of steel inside the concrete. Okay, and that normally is done by providing the steel in the compression zone. So if a beam requires to resist a greater bending moment than the singly reinforced beam, then we need to provide a doubly reinforced section in that case. Second situation is there when we have to provide or design a beam which is continuous over several supports. In MOS 1 or MOS 2, you have learned about the types of beams, right? You have learned simply supported beam, then cantilever beam, then overhanging beam, and you also learn about the continuous beam. Have you studied the analysis of continuous beam? Analysis for finding the moments, bending moments? Students,
Yes, ma'am.
uh,
Yes, ma'am.
have you learned the continuous beam, analysis of continuous beam?
Yes, ma'am.
Have you learned it? Which method you have used to find out bending moments? Do you remember that?
I mean, in Moss 1, we have found the bending moment.
But for not for only simply supported or fixed beam or cantilever beam, you must have studied the continuous beams also, right? The beam which is having three supports.
Then
Do
for
you
that,
remember?
we have
Clapeyron's
calculated
three
the
moment
flexibility.
theorem.
Yes, correct. Clapeyron's three
Ma'am,
moment theorem.
Clapeyron's three moment theorem.
Correct,
Yeah.
correct, correct. So if you recall the analysis of continuous beam, suppose we have considered the example of a continuous beam in which there are two spans. Okay, two spans means there are three supports. Okay, ABC is a beam I'm considering at A, at B, and at C. Everywhere there is a simple support. So beam is continuous over a support B. So if you recall the bending moment diagram for this particular beam, at the support B also we are getting certain bending moment. And that comes normally a sagging bending moment. Am I right? Are you able to recall that beam? Are you able to imagine the beam? Students, are you there in the class?
Yes, ma'am.
Yes.
Huh. So
Yes, ma'am.
over the support B, when we draw a bending moment at the support B also, in case of continuous beams, we get a certain bending moment, which is normally a sagging or positive bending moment. And for the mid span, we get a negative bending moment. Okay. So as the positive bending moment is there acting at a support, in such cases, for continuous beam, we need to provide the reinforcement in the compression zone also, because the beam has to resist the positive moment at the support also. That's why when we have to design a continuous beam, we always design it as a doubly reinforced beam. Third situation is that when a beam or a member is subjected to reversal of stresses. Now, what do you mean by reversal of stresses? Do you have any idea about this concept? Reversal of stresses?
No, ma'am.
Okay. Uh, have you learned trusses? I'm shifting directly to the steel member now, but that is the simplest example to explain the concept of reversal of stresses. Have you learned trusses?
Yes, ma'am.
Huh. So when you analyze a truss, in each and every member, we calculate a force. And that force is always in the form of an axial force. The nature of the force will be either compressive or tensile. Right? Am I right?
Yes, ma'am. Yes, ma'am.
So, if we have consider any particular example of a truss which is subjected to vertically downward load, I'm specifically mentioning the direction of the load, that the loads are acting vertically downward. If you consider the example of a dead load and live load, these loads always act in vertical downward direction. But wind loads, they don't always act in a vertical downward direction. Sometimes they also act in vertically upward direction. Wind, how it blows, whether it is blowing at 90 degree to the given structure or parallel to the structure, or that is 0 degree or 180 degree or 45 degree, we cannot predict the direction of a wind. And hence the effect of the wind load on the structure, in terms of the load, if we want to find out, it will be either in the downward fashion or it will be either in the upward fashion. So the stresses developed in the structure also changes accordingly. Suppose if you consider any example of a beam, and on the beam there is a central point load which is acting vertically downward direction. Due to that, your beam will bend, right? It will bend in a concave fashion. If you recall the deflection diagram, okay, it will show a concave fashion deflection. But if the same force is acting in vertical upward direction, the beam will deflect in convex fashion. Okay, so depending upon the direction of the load, the stresses developed in the sections or in the members also changes. If your wind load is acting vertically downward, the beam will deflect in a downward direction. If a force is acting vertically upward, the beam will deflect in a vertical upward direction. Okay, this is called as reversal of stresses. Particularly when we design the trusses, we have to always consider the reversal of stresses concept. Because in case of industrial structures or the high-rise structures where the wind has a major impact on a structure, the direction of a wind keeps on changing. Either it will work in the downward direction or it will work in the upward direction. In that case, the same member we have to design for both these effects by considering the change of the stresses. What is that effect? See, if your wind load is acting vertically downward on the truss, the tie members of the truss are always will be subjected to tension. If the load is acting vertically downward. If the load will start acting vertically upward, your tie member will get subjected to compression. There will be axial compression in tie member sections or in tie members. Okay, so this is called as reversal of stresses. For one direction of a particular load, when a force in a particular member has an axial tension nature, the same force or the same member, the force nature of the force in that particular member will become exactly opposite when the force direction or the external loading direction changes. This is called as reversal of stresses. So when a member is subjected to reversal of stresses, we need to provide the reinforcement in the compression zone also. So in that case, we have to design doubly reinforced section. And the last condition, that when a member is subjected to shocks or impact of accidental lateral thrust, okay, or in simple fashion, when a particular beam is subjected to impact loading, to carry that impact or to sustain that impact safely, we need to design the beam as a doubly reinforced section. Okay, so when you start your term work, your project for a term work, and when you observe the various types of beams within your residential plan, you have to check for the conditions, whether my beam is continuous. If it is continuous, then I have to go for doubly reinforced section. Whether my beam has a restriction of the dimensions, in that case also I have to consider the doubly reinforced section. Okay, for residential buildings, as we are considering only dead load and live load, we know that the direction of the load is fixed. It will act vertically downward always. So there is no question of reversal of stresses in case of residential building of a lesser number of stories. That is, we are designing G+2. So for G+2 building, reversal of stresses will be, the chances of reversal of stresses will be least. So we do not consider reversal of stresses for G+2 building. But if we are designing a high-rise structures, okay, like say a 40-story, 45-story building, in that case, definitely the wind will come into the picture, wind force. Okay, we have to design that structure for wind force also. And there we have to take into account the reversal of stresses. And accordingly, we have to change the design of the structural members. Is it clear to everybody why or when we need to provide the doubly reinforced section? Is it clear?
Yes, ma'am.
Okay. Now, along with the assumptions of limit state for flexure, for doubly reinforced section, two more additional assumptions are considered. The first one is that the stress strain curve for steel is same in tension and compression. Okay, we have learned about the stress strain relation of for steel by considering the steel is in tension zone. Okay, why it is mentioned? It is assumed that the steel will behave in the same fashion when it is in tension and when it is also in a compression. See, we have changed here the stress development. It is a reversal of stresses. Tension test and compression test. These are exactly the two opposite tests. But in both these conditions, it is assumed that the stress strain curve for steel is same. Okay, this is the assumption. And because of that, we can refer the same curve for calculation purpose. In the stress Fy in the steel and modulus of elasticity of steel Es is also same in tension and compression. Obviously, the steel which is in compression zone, it has to carry the compressive forces or compressive stresses. When it is when the compressive stresses are developed in the steel, in that case also the modulus of elasticity value E is same, that is 2 into 10 raised to 5, and the yield stress Fy developed is also same, that is either 250 or 415 depending upon the grade of the steel. So these are the two additional assumptions made in case of doubly reinforced sections. Now let us see and understand the concept of doubly reinforced section through this diagram. So this particular diagram shows first the cross-sectional view of a doubly reinforced beam, in which along with a steel which is provided in a tension zone, the steel is provided in compression zone also. Okay, so this is a cross-section of a beam with width B and effective depth D. The area of the steel in tension zone we represent by the notation AST. Area of the steel in compression zone sorry, we represent by a notation ASC. Okay, area of the steel in compression. Now we have discussed in previous lecture about the cover to the reinforcement. Okay, last time I have explained you that the distance from CG of the reinforcement steel to the bottom of the beam, this particular distance is called as cover to the reinforcement. When we measure the cover from the CG of the steel, it is called as effective cover. When we measure the same distance from the bottom of the steel, it is called as clear cover. Okay, in the same fashion, in the compression zone also we have to show this cover as the cover to the compression steel, which is denoted by DC. Okay, so this is actually the cover to the compression steel denoted by DC. This is our strain diagram, which will remain as it is. The values of epsilon C, epsilon S, etc. The depth of neutral axis is denoted by XU. Now let us come to the stress diagram. What will happen with the stresses? See, in the compression zone, in case of singly reinforced section, there was only concrete. Now, in case of doubly reinforced section, two materials are there in compression zone. One is the concrete and another is steel. So, the force of compression developed in a compression zone has to consider by the force developed by both these material. One is developed due to the concrete and another developed due to the steel. Okay, so the expression for Cu changes here for doubly reinforced section, which is equal to Cu1 plus Cu2. Obviously, Cu1 is the force of compression resisted by one material, and force of compression Cu2 will be resisted by the another material. I am not specifying here a specific material. I'm not calling a name of the material here. I'm simply talking it as one material or another material, just for your understanding. But this is not the true condition. When we do the analysis of doubly reinforced section, we have to consider the same section in two methods or in two modes. How it is considered? It is considered that it is made of two sections. Okay, the same section is made of two sections. Section 1 is considered as a singly reinforced section with concrete resisting compression Cu1 balanced by the tensile force Tu1 provided by tension steel AST1. The moment resisted by this section is denoted by Mu1. Second section is assumed as an imaginary section which consists of compression steel providing additional compression force of Cu2, which is balanced by tensile force Tu2 provided by tension steel AST2. The moment resisted by this section is assumed as Mu2, and the total moment is Mur, which is addition of Mu1 and Mu2. But initially we don't know what is Mur. So Mu1 is calculated first and then Mu2 is calculated by using this formula. Okay. Now whatever the explanation is written here, it will be best understood by this diagram. This is the doubly reinforced section, the entire section. The same section is considered to be made of two sections. Section 1 is the one which is our singly reinforced section. Okay, that is the steel is provided only in the tension zone and there is no steel in the compression zone. But actually there is a steel. So what we are doing, we are providing a hole here, because at this place we are assuming initially that in section 1 there is no steel in the compression zone, but there is not concrete also here. So we are keeping these holes as it is. Okay, so these are the holes, hollow parts in the compression zone. Okay, this is the section 1. And section 2 is assumed as an imaginary section in which there is only the compressive steel in the compression zone. It means there is no concrete in the compression zone. In the compression zone, there is only the steel, compressive steel. And in the tension zone, again, there is only the tensile steel. Now, this total AST it is assumed that it is distributed in such a fashion that half of the steel percentage of steel is considered in section 1 and remaining is considered in section 2. So we are distributing the total AST in both the section in such fashion that the force of compression developed by the concrete in a compression zone is balanced by this AST1, and the force of compression developed by the steel in a compression zone, it will be balanced by the steel provided in the tension zone. Is it clear to everybody? Because understanding this concept is very important. All further formulas are based on this concept only for doubly reinforced section. So do you have any doubts in this?
When we don't do half of that, no, whatever the force will be of the concrete, we will take as equal to AST1 and remaining we will give as to AST2.
But how we are, see, for sake of simplicity, hello?
Yes, ma'am.
Huh. For sake of simplicity of calculations, we are considering that the entire doubly reinforced section is made of two sections. One is a singly reinforced section, but actually in this singly reinforced section, at this portion there is no material, it is completely hollow. Okay, but our assumption is that there is no steel in the compression zone. So whatever the compressive force developed by this concrete, it will be balanced by the tensile force developed by the steel provided in tension zone. Now, obviously, in this particular beam, the force of compression is developed by both these materials, by concrete and by steel. Okay, so whatever is the value, it will always balance the steel, the tensile force provided by the steel. But for sake of simplicity, we are dividing this force of compression into two parts. The one which is resisted by concrete only and the another which is resisted by steel in compression zone only. Now, as the Cu force we are dividing into two parts, Cu1 and Cu2, Tu also we need to divide into two parts. Otherwise, there will be no equilibrium in any section. Are you getting this?
Yes, ma'am.
Huh. So when we consider Cu1, it will be Tu1, the equivalent or not equivalent, but the balancing force. And when we call Cu2, there will be a balancing force of Tu2. So the tension steel in a tension zone, we consider distributed in this fashion, that Tu1 is balancing Cu1 force and Tu2 is balancing Cu2 force. Is it clear now?
Yes, ma'am.
Okay. So these are the corresponding stress diagrams. This is actually the stress diagram for our doubly reinforced section, in which we have shown the maximum stress in compression as 0.446 FCK. The total force of compression Cu is Cu1 plus Cu2, and total force of tension is Tu, which is equal to 0.87 Fy AST. Okay. Now the same stress distribution diagram, we consider that it is divided into two parts by considering the stress distribution diagram corresponding to section 1 and stress distribution diagram corresponding to section 2. So in the section 1, we are considering that only the Cu1 is in action. Okay, the force of the compression developed due to concrete is in action. So to balance Cu1, there will be some force Tu1, which will be 0.87 Fy into AST1. Okay, and the second section, the force of the compression, see here, the stress distribution diagram is simply a vertical line over here, because we are representing the force of compression only at the level of compression steel here in the compression zone. And stress in the steel, we consider that it is concentrated at the level of the steel only. So here, along with our entire beam section, at this particular level, we are considering that the stresses are concentrated. So it is simply shown by a straight line, straight vertical line, and the force of compression, this is developed due to the steel present in a compression zone. Okay, so this Cu2 will be balanced by Tu2, that is the force of tension developed by the tension steel. So the tension steel we need to divide like AST1N and AST2. Okay, Is it clear? So Cu1, as the force of the compression is developed due to concrete, its expression will remain same, that is 0.36 FCKB into XU. But Cu2 is the force of the compression developed by the steel present in the compression zone. So it will be stress in the steel multiplied by area of the steel in compression. Okay, so the stress in the steel in a compression zone is represented or is denoted by the notation FSC, and area of the steel in compression zone is denoted by notation ASC. So the force of compression developed by the compression steel is given by FSC into ASC. Is there any doubt with this stress distribution diagram?
Shouldn't that FSC be instead of FSC? Can we write 0.87 FY?
No, no, because 0.87 Fy is the design tensile stress, okay, and that is developed in under tension. That is developed under tension. Now, FSC value, its maximum value is limited to 0.87 Fy. That is true. As per the assumption, the stress developed in a compression steel is considered as same that of the tension steel. That is our assumption. So, up to certain level, what you are saying is correct. That FSC value we can consider 0.87 Fy, but that is the maximum value. Actually, when we provide the steel in a compression zone, the amount of steel in a compression zone always comes out to be lesser than the amount of steel provided in the tension zone. So if I will go back to the diagram of this cross section, you can see here I have shown three bars here in the tension zone, whereas in compression zone I have shown only 2 bars. So it is always true that when we design a doubly reinforced section, the ASC is always lesser than AST. So the stress developed in a compression zone steel, that is FSC, always either come less than 0.87 Fy or it is equal to 0.87 Fy. That's why we cannot directly put the value of FSC here as 0.87 Fy. It may be equal to or may not be. It will be either less than or equal to 0.87 Fy. So that depend upon how many steel or what is the percentage of steel we have provided in a compression zone.
Then we can also provide the same number of bars in compression zone also. Can we?
Yes, yes, it depends on our design. It depends upon what is the external moment acting on a beam. What is the dimension of a beam we have provided. All these we have to consider, and accordingly then we decide how much percentage of steel we have to provide in the compression zone. But keep in mind that percentage of steel provided in a compression zone will be always equal to or less than the percentage of steel provided in tension zone. It will never exceed the percentage of steel provided in tension zone.
And then what does that suffix U denotes? CUTU.
U stands for ultimate.
Okay.
Ultimate force, ultimate compressive force, ultimate tensile force, ultimate moment of resistance. Is it clear? Any more doubts?
No, ma'am, no doubt.
Shall I proceed further?
Yes, ma'am.
Okay. So let us see now how to find out the depth of neutral axis. Again, as in case of singly reinforced section, we need to understand we need to derive the various formulas. That is for XU, what will be the formula? For MUR, what will be the formula? How to find out the percentage of steel, that is the expression for AST. Now, additional ASC expression also we need to find out here in case of doubly reinforced section. And also to find out the type of the section based on the XU value. So let us find out first the depth of neutral axis. For that, when no external force is acting on a beam, for equilibrium, we know that the total compression in a compression zone should be equal to total tension to have a equilibrium in the beam section. So we will equate now the total force of compression, which is now addition of two compressive forces, Cu1 plus Cu2 equal to Tu1 plus Tu2. Now the expression for Cu1 is given as the force of compression given by concrete. which is 0.36 FCK B into XU, plus CUT is the expression of the compressive force given by or developed by the steel present in the compression zone. Okay. Now here FSC into ASC, this formula we have seen. If I will go back to the earlier diagram here, CU2 is FSC into ASC. But if you consider this diagram, this diagram, here actually we are considering the force of compression developed by the concrete and force of compression developed by the steel. In this section, at this location, no material is present. So the stress related to this particular part or area we need to subtract. And that's why this expression includes FCC. Now this FCC is the compressive force or the stress in the concrete in compression zone. FCC stands for stress in concrete in compression zone. So that stress is actually the stress related to those two hollow holes. Okay, so that we have to subtract, and hence why the expression is FSC minus FCC into area of the steel in completion. That will be equal to TU1 plus TU2, that is 0.87 FY AST1 plus 0.87 FY AST2. So let us simplify the terms and we get the expression for XU as XU equal to 0.87 FY AST1 plus AST2 minus FSC minus FCC into ASC divided by 0.36 FCKB. It is very simple that I have shifted this entire term to the right hand side. Okay, so addition of these two is 0.87 FY. I have taken common AST1 plus AST2. This I am shifting to the right hand side, so it will be minus FSC minus FCC into ASC, and the term along with XU will come to the denominator 0.36 FCKB. Is it clear how we are getting the expression for XU? It is
Yes,
simple
ma'am.
mathematics. Now, if you consider this term FCC, as I have explained, it is a stress in concrete in the compression, which is 0.446 FCK, and FSC is the stress in the steel in compression. Now, in actual practice, this deduction of FSC into ASC is ignored without much loss of accuracy, and hence the one mistake I have made. I just want to make the correction here immediately. This FCC term okay, this FCC term is ignored. So FCC into ASC, this multiplication is ignored in the calculation because that value is very, very small. See, if you have provided say just 20 mm diameter bars and there are two holes of 20 mm diameter as compared to the entire width of say 300 mm. So that much area, when we consider FCC into ASC, that stress, it comes very, very small value. And even if we ignore that value, it doesn't have any impact on the final XU value. So we do not compromise to the accurate results or accuracy even when we ignore this particular term. So for sake of simplicity of the calculation, we simply consider the expression for XU as 0.87 FY into bracket AST1 plus AST2 minus FSC into ASC divided by 0.36 FCKB. Is it clear to everybody? Expression for XU.
Ma'am, in this case, we are not considering the compression due to the concrete, the whole part, upper part.
No, upper part is there, na? It is 0.36 FCKB is there. We are only ignoring, see, whatever is this diagram, we are only ignoring the stress developed in these two regions. At this region, where there is a hole, we are ignoring this particular region of section 1. Okay?
Yes.
Any other doubt to any other student? Or only Omkar is present in the class? Omkar is asking me all these doubts, right? Hello, guys.
Yes, ma'am.
Ma'am.
Who was asking me all these doubts?
Am I? Omkar?
Your name is Omkar, na?
Yes, ma'am.
I started identifying now based on your voice. Huh? Okay. So all other students are not getting any doubt. So I hope it is clear to them very perfectly. Let us move to the next slide. Now let us find out how to calculate the moment of resistance. Now to find out the ultimate moment of resistance, which is given as MUR, which is the summation of MU1 plus MU2. MU1 is the moment of resistance given by the section 1. MU2 is the moment of resistance given by section 2. So again, either we have to use the expression Cu1 into Zu1 plus Cu2 into Zu2, or Tu1 into Zu1 plus Tu2 into Zu2. Obviously, for doubly reinforced section or any beam in limit state of collapse, the final failure is considered as a failure of a concrete only. So for doubly reinforced section, we consider the expression for moment of resistance by this formula only. That is Cu1 into Zu1 plus Cu2 into Zu2. Okay. So now what is Cu1? This expression we already know. What is Cu2? We know this expression. What is Zu1? Zu1 is this distance, lever arm. So how to calculate Zu1? It is simply the total effective depth D minus 0.42 XU. Okay. What is Zu2? Zu2 is the lever arm. Again, the distance between Cu2 and Tu2. Here in this diagram, Zu2 will be calculated as total effective depth D minus DC. DC is actually the cover to the steel present in compression zone. Okay. So the expressions become like this. MUR is equal to Cu1 0.36 FCKB into XU into Zu1, this value, which is D minus 0.42 XU, plus Cu2, which is FSC into ASC, into Zu2. Zu2 is D minus DC. Okay, so this is the final expression for MUR. Are you writing down these formulas in your notebook?
Yes, ma'am.
Okay. I hope you have written the expression for XU also, and write down now the expression for MUR. Is it over? Shall I proceed?
Yes, ma'am.
Okay. Now let us see how to find out the area. Now area of the steel. Now the steel is present in tension zone also, and it is present in compression zone also. So let us first find out how to calculate the area of the steel in tension zone, or in other words, area of the tension steel. For that, we have to consider only section 1. Recall the diagram of section 1, cross-sectional view of the section 1, in which the section 1 develops the moment of resistance equal to Mu1, which is given by Tu1 into Zu1. So what is the expression for Tu1? It is 0.87 Fy into AST1. Zu1 is D minus 0.42 XU. So this is a simple formula. So from this formula, find out AST1. So it is Mu1 divided by 0.87 Fy into bracket D minus 0.42 XU. Now this is just a area of a steel in tension provided in section 1. Now the area of steel in tension provided in section 2 also there, which is denoted by AST2. For finding that, we have to make use of Mu2. So Mu2 is equal to Tu2 into Zu2. Simply putting the values, we get AST2. Again, there is a correction. Let me correct immediately. AST2 is given as Mu2 upon 0.87 Fy into Zu2 is d minus dc. Okay, so total area of the steel is given as AST1 plus AST2. These formulas are important to understand and also keep in mind because these will require further when we start actually designing the beams. This is just you are learning right now the analysis, huh? How to find out MUR, how to find out XU, AST formula. This is analysis. Next part of your unit 2 is related with your design, in which you will be only having a value of moment of or the bending moment, external bending moment. All other values, B value, D value, AST, ASC, everything you have to decide based on your design assumptions. Okay, so this is about the area of the steel in tension. Now let us see area of the steel in compression. Now to find out the area of steel in compression, we have to make use of concept that the total force of compression is equal to total force of tension. Now obviously the area of compression steel we are assuming in a section 2. So we have to consider the force of compression shown by the section 2 equal to force of tension by the section 2. That's why Cu2 is equal to Tu2. This diagram we have to consider. So what is Cu2 here? Cu2 is FSC into ASC. Tu2 is 0.87 Fy into AST2. So simply equate these expressions and we can get ASC here. Again, in this calculation, we neglect this term FSC. Okay. So, or in other terms, I can say we are using only these two expressions here. So 0.87 Fy into AST2 divided by FSC, it will give me the area of steel in compression zone. Or the same expression we can find out by the concept of mu2. Okay, mu2 is equal to cu2 into zu2. So simply putting the value of cu2 over here, we can find out ASC as mu2 upon fsc into d minus dc. Is it clear how the area of compression steel is calculated? These are the two ways how we can derive the expression for ASC. In both the fashion, the final value of ASC will remain same. Is it clear to everybody?
Yes, ma'am.
Now, what is the expression for XU? Let us recall it quickly. Anybody from you can tell me the expression for XU for doubly reinforced section. XU equal to
0.87 Fy, AST1 plus AST2 minus FSC into ASC divided by 0.36 FCK into B.
Correct. Now in this expression, there are some constant terms like 0.87, 0.36. There are some constant values for the given section of a beam, that is the B width value. So B value will remain constant if a given section or the section is given having a certain specific dimensions. For the specific beam, the other two parameters will also remain constant. The two parameters are FCK and FY. FCK is the grade of the concrete and FY is the grade of the steel. So for given section having specific dimension, specific grade of steel and specific grade of concrete, all these terms will remain constant. Now what is variable in this expression? AST. Okay, AST will also remain constant if we know the number of bars present in the tension zone. ASC will also remain constant if we know how many number of bars are there in the compression zone. The second variable or the last variable is FSC. FSC is the stress developed in the compression steel, and that expression we need to derive now. How to find out FSC? If I want to find out XU, all other values just now we have discussed how to find out AST, how to find out ASC, FY, FCKB, these are the values which will be given in the problem statement itself. Now the term remaining is FSC. Let us see now how to find out FSC. FSC is nothing but the stress in compression steel. And to find out this, we have to consider this concept that the stress in compression steel depends upon the strain at the level of compression steel. So if you remember, our second or third lecture, in which we have discussed about the stresses developed in the members and the stress distribution diagram for the given section. In that, we have discussed, or we have derived the expression for XU by considering the strain diagram itself. In the same fashion, when we want to find out the stress developed in the compression steel, we have to consider the corresponding strain. So we have to make use of the strain diagram here to find out the FSC value. Here in this strain diagram, the strain in the concrete is shown here, epsilon Cu. The strain in the tension steel is also shown here as epsilon S or epsilon Sy. Similarly, the strain in compression steel is shown at the level of compression steel, which will be somewhere here, okay, which is denoted by epsilon Sc. So by making use of this strain diagram, now we want to find out what is the expression for epsilon Sc and what is FSC. FSC is the stress in steel in a compression zone. So we already know the relation between stress and strain by Hooke's law. What is that? Can you recall the Hooke's law?
Stress directly. In an elastic limit, stress is directly proportional to strain.
Correct. Stress if we represent by F and strain we represent by epsilon. So the ratio F upon epsilon is a constant. And that constant term is identified as yes.
Poisson's
What
ratio.
is sorry?
Poisson's ratio.
Wrong.
Stress upon strain.
Stress upon strain is equal to
Modulus of elasticity.
correct. It is denoted by
E.
capital E. Capital E. Okay.
Yes.
So F upon epsilon is equal to capital E. This relation we know. So if I know what is epsilon, I can find out F value because I know the E value, it is constant and it is always taken as 2 into 10 raised to 5 Newton per mm square. Am I right? Are you getting my point? Students.
And can you repeat this sentence?
See, Hooke's law, what is the Hooke's law, or as per the Hooke's law, I can write down one particular relation as F upon epsilon is equal to E. F is the stress, stress upon strain is equal to constant term E, right? So stress I'm representing as F, strain I'm representing as epsilon, F upon epsilon is equal to capital E. So if I know what is the epsilon value, I can find out F value. Are you getting this now?
Yes, ma'am.
The same concept we have to make here, or make use of this concept here to find out the stress in steel in the compression. So to find out that, I have to find out what is the strain in the steel in compression zone, which we are denoting here as epsilon Sc. So by making use of this strain diagram now, let us find out the expression for epsilon Sc. Here there are two similar triangles. So using concept of similar triangles, I can write down these expressions. Epsilon C upon XU is equal to, what is epsilon C? Epsilon C is this. So epsilon C upon XU will be equal to epsilon Sc upon this depth. Now how I can find out this depth? This is total XU minus DC. I can get this depth. Are you getting this?
Yes, ma'am.
So in this upper portion of the strain diagram, I'm considering two triangles, the bigger one and the smaller one. In the bigger diagram, considering the similarity of the triangle, epsilon Cu upon Xu will be equal to epsilon Sc upon this depth, which is Xu minus Dc. So same is written over here. Epsilon C upon Xu is equal to epsilon Sc upon Xu minus Dc. Epsilon Sc is the strain in the concrete and its value is fixed. And that value we already know that it is 0.0035. So I'm simply putting that value over here, 0.0035. Okay. And I'm sorry, epsilon C value. We are interested to find out epsilon Sc value. So I will shift this denominator to the left hand side, and after simplification I will get this expression. Epsilon Sc is equal to xu minus dc upon xu into epsilon c, and its value is fixed, which is 0.0035. So I simply put the value of epsilon c here as 0.0035 into xu minus d upon xu. This is giving me the expression for epsilon sc. Okay, so further I have simplified the same term as xu. I have divided to the numerator. So xu upon xu, it is coming 1 minus dc upon xu. In a simple format, I have written the same expression here. So this is the expression for strain in compression steel, epsilon sc. So you just note down this expression in your notebook. This is very important expression. Epsilon sc is equal to 0.0035 into bracket 1 minus dc upon xu. Now, if you consider the expression for strain, that expression consists of xu term. Okay, and based on epsilon, we have to find out the stress. Now, again, I have whatever I have explained about the Hooke's law, stress upon strain is equal to constant. By making use of this relation, we can easily find out now FSC. Okay, so for mild steel, the stress strain relationship is linear up to the FYD, that is up to the yield strength, and further a strain, as the strain increases, the stress remains constant. Hence, the relation between FSC and epsilon SC can be obtained by using this concept. Okay, the same which I have explained just 1 minute earlier, that the stress upon strain is equal to constant. So stress is FSC is equal to epsilon SC into ES. ES is the modulus of elasticity for steel, which is taken as 2 into 10 raised to 5. Now this entire FSC value is limited to the maximum yield strength value, which is given as 0.87 Fy. Okay, so let us put the value of epsilon SC, which we have calculated here in earlier slide, 0.0035 into bracket 1 minus dc upon xu. So that value is here replaced here as epsilon SC into ESC. ESC is 2 into 10 raised to 5. So after simplification, we are getting FSC expression as 700 into bracket 1 minus dc upon xu. Is it clear to everybody?
Yes, ma'am.
Now, this expression we have simply derived for mild steel. I have purposely written this for mild steel because if you recall the stress strain curve for mild steel, it is completely linear. Okay, the stress strain curve for mild steel is linear till the stress reach to the Fy value or the design strength of the steel, and further that or beyond that, it is considered that the strain is constant and the stress is also constant. Okay, so if you recall the stress strain curve for mild steel, it is completely linear, and hence we can use the Hooke's law here, which is also applicable for the elastic limit only, within elastic limit. And within elastic limit means if the relation between stress and strain is linear, then only we can use that particular concept. Now the same concept we cannot use for HYST bar, because for HYST bar, if you recall the stress strain curve, it is somewhat like this. Okay, it is linear up to certain point, and beyond that it becomes non-linear, and further the strain value remains constant. So for HYST bar, this simple concept of stress upon strain equal to constant cannot be used directly. Okay, the value of FSC in this case is needed to calculate in a trial and error method, by a trial and error method. And how to calculate this trial and error method, that we will see in the next lecture, because it will consume at least 15 to 20 minutes more to understand the concept. Okay, so I will stop today here. I will give you the attendance link in your chat box. And in the next lecture, that is during your tomorrow's lecture, we will discuss about the expression for FSC for HYST bar. So all of you are requested to give attendance through the given link only.